Speaking of programmable system-on-chip, modern FPGAs are no longer just a bunch of reconfigurable elements. They can contain DSPs, reconfigurable elements, and general-purpose processor, which can be both physical CPUs embedded in the FPGA fabric or soft cores mapped on a part of the FPGA. On one hand, the heterogeneous nature of a programmable system-on-chip, characterized by the coexistence of both software executed on at least one GPP and hardware implemented on a reconfigurable logic element, can be found back in the years in Xilinx Virtex 2 Pro devices, where an IBM PowerPC 405 was embedded in the FPGA fabric. Since then, a lot has been done. An example of this is what it has been known under the code name of Stellarton, the Intel Atom E6XX processor family. Intel and Altera made a deal to distribute a chip that has both an Intel processor and an Altera FPGA in the same package. From the outside, it is nothing more than a single chip, but underneath, it's actually two separate chips that are co-sharing the same package. Another example is the Xilinx Zing 7000, all-programmable SoC family, which integrates the software programmability of an ARM-based processor with the hardware programmability of an FPGA, enabling key analytics and hardware acceleration while integrating CPU, DSP, and mixed signal functionality on a single device. Built on the success of the Zing 7000 all-programmable SoC family, Xilinx designed the ultra-scale MP-SoC architecture. The ultra-scale multiprocessor system-on-chip, or MP-SoCs, extend the Xilinx system-on-chip to enable true heterogeneous multiprocessing with the idea of being able to implement the right engines for the right task, to implement smarter systems. Furthermore, the ultra-scale MP-SoC architecture provides multiple advanced processors that scales from 32 to 64 bits with support for virtualization. On the other hand, in terms of soft cores, Xilinx provides a micro-based and a pico-based soft core processor to be used in systems implemented within their FPGAs. A second example is the Leon project, which was initiated by the European Space Agency in late 1997 to study and develop a high-performance processor to be used in European space projects. The objectives for the project were to provide an open, portable, and non-proprietary processor design capable of meeting future requirements for performance, software compatibility, and system cost. There are also other FPGA companies but Xilinx who design their own soft cores. This is the case for the Nios 2 processor designed by Altera and of the LM32, which is a configurable soft core specifically optimized for lattice semiconductor FPGA devices. A lot has been also done around the RISC architecture. The Open RISC 1000 architecture has been started from an initiative to develop a freely available RISC architecture. For the first few years, the project was backed by their employer, Flextronics, who produced an ASIC version of the design. Since the very beginning, the project was led by an independent community, opencourse.org. While opencourse.org hosts over 1,000 projects today, the Open RISC 1000 remains its flagship project. RISC processor designs date back to the early 1980s and have always been of academic interest. Academics created the original RISC instruction set, DLX, for use in the first edition of the Hennessy Patterson textbook, Computer Architecture, a Quantitative Approach, in 1990. However, this instruction set architecture was intended primarily for educational use. The RISC-V instruction set architecture is the fifth generation of this original work, and it's quite suitable in both commercial and academic environments.